Hello, I'm going to tell you about a method for computing moments in random deep neural nets, and this is based on joint work with Boris Hannon, who's now at Princeton. So to fix notation, I'm going to look at networks that have depth d, and the widths I'm going to call with n, so there's going to be n0, that's the input width, n1, n2, n3, and so on are the intermediate layers, and nd is the output width. I'm going to define one other thing that you might have not seen before, and that is the depth to width aspect ratio. So I'm going to call this with beta, and this is sort of the ratio of d to n, but of course there is no one n, so this is how we define it, the sum of 1 over ni. So with that network architecture fixed, and it's going to be a fully connected network, by the way, although I think the method could easily work for any other type of sort of architecture that you might imagine. But once you have the architecture fixed, we're going to have weight matrices at every layer, we're going to have bias vectors also at every layer, and we're going to combine them in the usual way with a nonlinear activation function applied entry-wise at every layer. So that's our neural network. Once you have the neural network, we're going to define something called the input-output Jacobian, which is just the output of the derivative of the output with respect to the input. So there's it makes an nd by n0 matrix, nd being the number of output dimensions and n0 being the number of input dimensions. And the result I want to tell you about is for this input-output Jacobian. And the result works for ReLU networks, so it has to be the nonlinear activation function, which is the ReLU. And the W's and B's are chosen randomly, so it's going to be a statement for random neural networks. And the statement says that something about the vector that you get by applying this input-output Jacobian to some vector. And for simplicity, I'm going to show you the result where you apply it to the vector of all ones, although we could extend it to any vector. So you take this input-output Jacobian, you apply to the vector of all ones, and you ask what its moments are, and we have a formula for that. If you take the norm of this vector and compute its 2kth moment, you get e to the 5 k choose 2 times beta, where beta was that depth to width aspect ratio. So some of these are a little funny. Where did the 5 come from? Hopefully you'll know by the end of the talk. The k choose 2 as well maybe looks a little funny at first glance, but if you have seen these kinds of things before, you might recognize these are the moments of a log normal distribution. So actually what this is saying is that at the level of moments, this vector J1 has the same distribution as a log normal distribution. So that's kind of why this result is exciting. And it even says something else, which is that the bigger beta is, the more crazy this vector behaves. So this kind of feeds into the vanishing and exploding gradient problem. And you'll know from this that deep networks must have much more vanishing and exploding gradients than shallow networks because of this result. So there's a couple technicalities. One is the W's and B's are chosen randomly. They have to have some conditions. One, they have to all be independent. They have to have finite moments of all order and no atoms. And this one is a little bit more of a technicality. They have to be symmetrically distributed, so they have to be equally likely to be positive or negative. And they should all be mean 0 and variance 2 over n. So this type of normalization you typically see on initialization of a neural network, so nothing too crazy here. Okay, so the proof I'm going to show you, there's 2 steps, and I'll try to sketch out a brief idea behind both steps. So step 1 is to relate the input-output Jacobian J to a random matrix product M. And step 2 is to use a path counting argument to find the moments of M. So I'll try to show you these 2 steps in a little bit of detail, but not too much. So the first thing is that this matrix J at the level of computing its norm is the same as computing the norm of this funny matrix M, which is a big product of random matrices. So the weight matrices W up here, but there's also these diagonal matrices that appear. So these are Bernoulli matrices. They're equally likely to be 1 or 0 on the diagonal with probability 1/2. And you do a big product of these. So by chain rule, it's not too surprising that you have a big product. The thing that is maybe a little surprising is that these Bernoulli matrices are independent of the W's, but it turns out that for ReLU networks, this is indeed the case. So the crucial assumption here is that it's for a ReLU network. And because of this ReLU fact, the derivative of the ReLU function is where these Bernoulli things come up. And because of the symmetric distribution, it turns out that they're all independent of each other. So it's a little bit of a miracle. And the proof technicality goes by doing some conjugation by Bernoullis and showing that it doesn't change the distribution. So a little bit of a funny thing to observe here, but for ReLU it all comes out very nicely. Okay, so that was step 1. And now step 1 turns the question into finding the distribution of this random matrix M. This is a big product of random matrices where we alternate the W's with these funny Bernoulli matrices. And it turns out that we can prove a limit theorem for the moments of this matrix M. Looks a lot like the one we had before, but now the 5 has been replaced with 3 over p minus 1. So the same kind of limit theorem we saw before, but now it's 3 over p minus 1. So of course when p equals a half, that's where the 5 comes from, and that's how the 5 comes into being. So I'm going to show you now, when we compute these moments, hopefully I can convince you where this 3 over p minus 1 comes from. And we have the same kind of assumptions as before. Okay, so let me show you a quick sketch of how we do this result. So we have to show the kth moment of this funny random matrix is this funny thing here with the 3 over p minus 1. And the proof is going to be some kind of path counting argument. I think of this as a kind of neural network version of the semicircle law proof with moments, if you know that. So let's start with the easiest possible case. I'll show you that case first. That's when k equals 1. And when k equals 1, we're just trying to show that the expected value of this thing squared equals 1. And of course, the normalization 2 over ni at each layer is chosen exactly to make this normalization work out. But let's see how it works out using path counting. So here I have a picture of our network. We got the layers W1, W2, W3. I have put the Bernoulli entries, so from each diagonal Bernoulli matrix, I've put those sort of at the vertices of this graph, so on the nodes here. And I think you should think of, what I'm going to try to convince you is that the matrix M you can think of as something involving paths in this graph. So in particular, if you put the weight WAB on each edge here, and you put the random variable x on each vertex here, then a path like this represents something from the matrix M. So, and in fact, the matrix M, the entry MAB, so the AB entry of the matrix M, will be the sum over all possible paths starting at B in the input layer and ending at A in the output layer. So here I'm doing a plot of M31. Or rather M13. So if you sum over all paths that start here and end here, that'll give you M13. And to sum a path, you have to multiply everything that you see along that path. So multiply all the edges, multiply all the nodes, and that'll give you M13. And why is this useful? Because now we can start doing little pictures here. So when we compute things involving M, it's going to turn into some kind of graphical picture involving paths going through this network, and we can sort of use our intuition about paths to make some progress. So the very first simple thing is if we try to compute M1 squared, this is going to be the sum over all pairs of paths. So the squared leads to pairs of paths. And we're going to be summing over all possible pairs of paths that start and end at the same point. So this vector 1 is exactly chosen to sum over all the inputs. Things have to end at the output by the way this is set up. So it's going to end up being all the pairs of paths that start and end at the same point. And we're going to do the expected value of that. And you might notice that when you do the expected value, almost every configuration of pairs of paths has expected value 0. And that's because when you go over an edge only once, like this edge has gone over only once, and you do the expected value, because the edges mean 0, you have no contribution from this. So what's left over, you have to go over every edge exactly twice. So what's left is pairs of paths that overlap. To summarize, if you want to do the expected value of M1 squared, you end up summing over all these paths, but the only paths that contribute are paths where both paths take exactly the same path and cover every edge twice. And so now it's quite easy to do the moment counting, because you just have to count the number of these paths. That's pretty easy. The number of paths is the product of the ni's. Now remember our normalization. We had a 1 over p ni for each weight w, and we had because these are Bernoulli random variables, they all come out with a p. And so if you put it all together, you count the number of paths, you multiply together all these expected values you see along the path, and that works out to exactly 1. And of course, that's how the normalization was chosen. So hopefully I've convinced you, modulo doing some work and checking all the things I'm saying, that the expected value of M1 squared is exactly 1. Now let's do the second moment. So let's do the expected value of M1 to the power 4. And this is where the 3 over p minus 1 comes out. This is the first situation where something interesting with 3 over p minus 1 is coming into play. So just like before, we have sums over pairs of paths, except now there are 4 paths because we're doing the fourth moment. And when you do the fourth moment, you have the same situation as before. The important thing is that all the edges have to be covered twice. If an edge is covered only once, it has no contribution. So here's a possible configuration. And now something interesting is going to happen is that there's going to be some kind of interaction between pairs of paths. So these yellow and green paths are somehow going to interact with the red and blue paths, and that's going to give us this 3 over p minus 1. So I'm going to think of sort of choosing some of these pairs of paths at random and calculating their contribution from their interaction. So we're sort of computing the expected interaction between two pairs of paths. So first remark, this kind of interaction where we have an edge covered up 4 times or something like that, this just does not happen very often. And that's because there's sort of not many paths where they can do this. So you'll have to take my word for it that this kind of contribution does not contribute in the final accounting. The thing that does contribute is when the paths collide like this at a single vertex. And when that happens, first of all, you get an extra factor of 1 over p. That's because we're only covering 1 Bernoulli here instead of 2. But then the other thing that can happen that's really interesting is that the paths can split themselves into a number of different ways. So there are 3 ways to group these 4 paths into 2 pairs. So there's the way they're coming out like here with the red and the blue together and the yellow and green together. But there's also another way, which is to do the yellow and the blue and the red and the green, or to do the green and the blue and the red and the yellow. So because of this combinatorial color switching that can happen whenever there's an intersection, you have this factor of 3 coming into play. So there's the factor of 3 coming from this combinatorics thing. There's the factor of 1 over p coming from the Bernoulli variable x. And so sort of you have this factor of 3 over p every time there's a collision. So after some bookkeeping, the expected value of m1 to the power 4 is exactly the expected value of choosing paths at random, 3 over p to the number of times these 2 paths will collide. And the number of collisions is somehow a sort of Poisson variable because in each layer there's n1 places where they could collide. So there's sort of like a 1 over nm1 probability they collide in layer 1, a 1 over n2 probability they collide in layer 2, and so on. And so after the final accounting, you end up with this nice formula, which is exactly what we want. 3 over p minus 1 summing over all 1 over ni. And that's where the 3 over p minus 1 comes into play. And if you understood the idea behind this proof for the 4th moment, you can really do it for any k. And that's because if you want to do the 2kth moment, what happens is now you have k pairs of paths, and the paths now can collide in k choose 2 ways. You have k pairs, any 2 of them can collide, and whenever they collide, you have this 3 over p factor just like before. So that's giving you where this k choose 2 comes from. So this is some sort of very rough sketch of how this idea is going, hopefully giving you the colorful picture of what's going on here. And I think I'll stop there. Maybe I'll give you the 2 archive links. So we used this once for the input-output Jacobian in this paper, and then we also used it for something called the neural tangent kernel in a more recent paper. So thanks very much. I'll stop there.